Okay, so now that we learned about the Metropolis Hastings, I'm going to put what I've learned to the test and do a couple experiments. I'll probably take a couple days to code it. I don't want you to have to sit through and watch me code everything. But we'll start off with one. We'll do a simple example. I'm thinking of just doing setting my target distribution to be a gamma and proposing a normal distribution, which should create my Markov chain. And hopefully, when it's done, it should represent a gamma distribution, the Markov chain. Next, I'll do a real world application. I'll probably do weather data. I have a weather example I'm looking at. And lastly, we will do some machine learning application using the Metropolis Hastings algorithm on a variational autoencoder on the MNIST dataset, which is they took several samples of people drawing numbers. And the VAE is a variational autoencoder. So as we know, the autoencoder takes an input space and performs dimension reduction on it into it takes the input down into a latent space, but variational autoencoder is Bayesian and is probabilistic. But we'll get into that. I'll walk through the code as when I'm done, and I'll be back. I'll see you soon. Okay, so here's our first experiment. We're just going to do a simple example. We're going to have our target distribution as a gamma distribution with a shape of 2 and a scale of 2. And we'll see what this looks like in the code here shortly. And for the proposal distribution, we're going to pick a normal distribution, which is very easy to sample from with a standard deviation of 1. And let's see what we have. Okay, here we have our first experiment all coded out here. We're just going to run through it real quick to make sure that we get the desired results. Just a proof of concept here. First, we're going to import all the packages we need for this to run. Then we set our parameters for our problem statement, a gamma distribution with a shape of 2, scale of 2. Next, I just want to see what the gamma distribution should look like with a scale of 2 and a shape of 2 to ensure that our final outcome resembles this distribution here. Um, Next, we're going to define our proposal distribution, which is a normal distribution with a mean and a standard deviation of 1. Then we define our target distribution, which should be a gamma. Next, we're going to initialize a starting point of 0. That's going to be the initial mean of our normal distribution. And we're going to change it throughout the loop. Next, we set the number of samples to generate, which is 10,000. If we want our Markov chain to be more precise, we can make this number higher, but for the sake of time, we're just going to keep it at 10. Then our samples, which is going to be an empty list. This as our algorithm runs, we're going to append the new samples into this list to create our Markov chain. Here's the algorithm. We're running through the we're creating a loop. Um, Now we're proposing our new candidate with our initial position, and as we accept or reject, this will change. Then we calculate the acceptance probability, which is the ratio of our proposal candidate divided by our target. Then we generate a random number using a uniform distribution between 0 and 1. Now, we accept or reject our candidate, our proposal. If it's accepted, we add the candidate into our Markov chain. If it's rejected, we just add the current sample into our Markov chain and keep running it until we finally get a sample that's accepted. Let's run through this real quick. See what we get here. Okay, and we're gonna plot it to see what our Markov chain looks like, and it should resemble a gamma, and it does. Let's see what it looks like if we increase the number of bins. It should be a little more precise. Typo, I'm sorry there. Excuse me. Okay, that that resembles our distribution. That's a pretty good result there. Let's go to our next problem to see what we come up with there. Okay, next problem here. We're gonna do a real life example here. We observe about 9 tropical storms in a year in Boca Raton, Florida, and we know the number of tropical storms per year can be modeled by a Poisson distribution with parameter lambda. The parameter lambda is drawn from a gamma prior distribution that has parameter alpha equals 7 and beta equals 1. If this is the only observation we have available, we could conclude that we observe 9 tropical storms per year, but in the Bayesian landscape, we have some knowledge about the rate parameters based on what we have observed in the past. Okay, cool, that's a bet. So what we're going to do here is essentially use a Metropolis algorithm to draw our posterior distribution based on what we have observed. So what I'm going to do here is, since we don't have an entire distribution, the distribution is unknown. I'm essentially going to use a normal distribution with a simple standard deviation of 1 and a mean of 0. I'm going to use that as a way to, since it's easy to sample from, I'm going to use that as a way to create a known posterior distribution. All right, here we go. So now that we have our defined goal here to try to estimate the target distribution or posterior distribution, which is derived using the Bayes theorem. This theorem states that the posterior distribution is proportional to the product of the prior distribution and the likelihood function. We're not going to worry about the normalization constant here in the denominator, because the beauty of the Metropolis-Hastings algorithm is we're operating off the assumption that we don't know what the normalization constant is. So in this problem, the prior distribution is the gamma distribution with parameters alpha and beta, what we see on the top right there. The x variable is going to be our lambda, and the likelihood function is a Poisson distribution in the middle left, in the top middle up there. This is our Poisson distribution with rate parameters lambda and observed data x, which is our 9 storms per year. So the posterior distribution is shown below, where the probability of our observed data giving our lambda is a likelihood function, and the probability of lambda is our prior distribution. The likelihood function for Poisson distribution with rate parameters lambda and observed data, which we see in the top middle. And the prior distribution here is the gamma distribution with parameters alpha and beta, and also lambda. Now we just combine these two and we should achieve our target distribution or posterior distribution. So we'll run this in the Metropolis-Hastings algorithm here in Google Colab and see if we get something desirable here. Let's have a run at it. Okay, so here's the code that I was able to come up with to resolve that problem here. Let's restore this, clear it out real quick. So we'll import all of our necessary packages to get this thing going. Next, we're going to initialize all of our constants. So our prior parameters are 7 and 1 for alpha and beta. Our observed data, we have 9. We're going to initialize a lambda to be 10 and the sigma to be 1 for our normal distribution, which we will be sampling from. Here is our target, our posterior distribution, our target, which we know is likelihood times our prior. Our likelihood is going to be a Poisson, so this is our reality. This is going to be our reality with our observed data being 9, and our prior distribution here, which is going to be a gamma distribution. This is where we will draw lambdas from that we will input into our reality or our likelihood, and this is going to be our target distribution. So here's our Hastings algorithm. We're going to run this bad boy by initializing chains, iterating from 1 to, we're going to do 1,000. We're going to sample from our normal distribution with the 1 as our standard deviation. We're going to get our acceptance probability, which is the minimum between 1 or the ratio of our proposed distribution divided by our current distribution. And we're going to sample a random number from 0 to 1 and do our acceptance or rejectance conditions. And we'll build our chain. So let's run this real quick. Should be fast, pretty quick. And here is our posterior distribution. This is our target distribution. So we know we can model the storms that we get per year with a Poisson distribution. This is but the highest or our mode of this distribution is like about 8, or it could be this. It's probably about 8. So we can model the number of storms we get per year from our mode, which is about 7.9. And the spread of this is going to be our uncertainty. So, okay, so now we're going to move on to our third and final experiment, which is going to be quite a bit more complex. We all know what an autoencoder is. It essentially consists of two parts, the encoder and the decoder. The encoder compresses the data from a high dimensional space to a lower dimensional space, which is also known as a latent space, which is shown here in the hidden layer, while the decoder does the opposite. It converts the latent space back to a higher dimensional space. This is often used in image compression, video compression, and even in tabular data when you think of like reducing high dimensional data to a lower dimension. So going from a tabular data set with like 1,000 features down to a new data set with like 100 features. The variational autoencoder is slightly different. It's a type of generative model that learns a compact representation of data into a lower dimensional space known as the latent space, and then it generates new data by sampling from this latent space. The simple autoencoder outputs latent vectors, but this does something different. Instead of outputting the vectors in the latent space, the encoder of a variational autoencoder outputs parameters of a predefined distribution in the latent space for every input. So here, if you look at the image to the right, you see it's outputting a mean and a standard deviation, which is outputting the latent distribution. The variational autoencoder then imposes a constraint on this latent distribution, which forces it to be a normal distribution. So you won't get anything, you won't get like an exponential distribution or Poisson. It's forced to be normal. The idea behind the latent distribution is that it allows for the variational autoencoder to capture the underlying structure of the data. So by training the variational autoencoder, the model learns the high dimensional data to a low dimensional data space in a way that preserves important information about the distribution of the data. This resultant latent distribution is a compact representation of the data, which can then be used to generate new data that is similar to the original data. And then, so you send an audio file to the variational auto encoder, it compresses it, and you can sample from this to produce the original data once again. The variational autoencoder, in the variational autoencoder, the latent distribution is typically assumed to be Gaussian distribution. And the decoder network is trained to map the samples from the Gaussian distribution back to the original space. And I know what you're thinking, that a Gaussian distribution is relatively easy to sample from because it's typically normal. But I want to try something a little complex here. I wanted to try mapping to five a five-dimensional Gaussian distribution, and you can try to imagine what that looks like in your head. Either way, I'd imagine a five-dimensional Gaussian is going to be pretty challenging to sample from. So regardless, sampling from a latent distribution of a variational autoencoder can be challenging, as the distribution is typically complex and high dimensional. The encoder network in a variational autoencoder is trained to approximate a true posterior distribution of the latent variables given the observed data. However, this approximation may not be perfect and may not provide a tractable form for sampling. So what I'm going to do is I'm going to train a variational autoencoder to reduce down to a five-dimensional Gaussian in the hidden latent space. So imagine this graphic on the right, imagine it here, but on the hidden layer, we're going to have five nodes in the hidden space to give us our five-dimensional Gaussian. And then from there, I'm going to use the MetroplisHastings algorithm to attempt to approximate the posterior distribution of the latent space. And then I'm going to just try to plot the results and see what we come up with, see if maybe it's going to be Gaussian, maybe not. But that's the purpose of research and experiment, so we can see the results of our thesis here. All right, let's give it a run and see what we come up with here.
Okay, so I'm going to go over the code that I was able to come up with here. This took quite a bit of time to develop, and a healthy amount of time to run as well. It took well over an hour and a half, 2 hours. Um, so I'll just review what we have. I started off by importing the packages to get this thing running. As a reminder, we're going to train it on the MNIST dataset. Put together a couple functions to help build the VAE, pre-processing the data set, sampling. I'll build my encoder, I'll build my decoder section, and I'll put them together to build a VIE with my hidden layer here. That's my hidden layer. Put together a function to calculate the loss. Next, I load the data with the test train, and I pre-process it. I initialize all my constants. Most VAEs have a latent space of 2 dimensions. I wanted to do something a little more complex and challenging, so I made my latent space have 5 dimensions. So we'll have a 5-dimensional Gaussian, whatever that looks like in your head. Hard to picture. Here I have compiled my model. Here's my model summary here. Pretty typical stuff here. I fit the model, 50 epochs. Now we get into the MetroplisHastings portion of it. Defined all my constants. Latent space, make sure it was 5. Initialize a starting point for my to build my Markov chain with a step size of 0.01. I initialize my Markov chain here. Number of iterations. I initially had this set to 10,000, but it took a while to run. I tried to drop it to 6. It still took a while. Whatever. So I've been looping through here, doing our MetroplisHastings algorithm, proposing a sample, calculating the likelihood of the current and the proposal, then doing acceptance probability, which is the minimum of either 1 or the ratio of the proposal divided by the current. Generated my random number, then my acceptance rejection, and appended that to my Markov chain. As you can see, this is we did a lot of iterations there, and this is what I came up with. This is the final result. Uh, I just did a scatter plot of the first two dimensions of the latent space, and this is what we have. I guess you could say it looks like a Gaussian bell shaped, but that's what we have. And here I tried to do a little histogram. We can do a histogram of each dimension there. It's not really Gaussian as I had hoped it to be, but I guess that one's kind of a normal shape. Let me see, first dimension. But yeah, that's what we have there. Hope this was very insightful for you. I hope you was able to hope you were able to learn something, and yeah, that is it. Thank you. Okay, so in conclusion, I just want to show a cool animation here of a multi-dimensional donut. You can see the Metropolis Hastings algorithm running on the donut, and you can see as it's accepting and rejecting samples, they're getting added to your Markov chain on the x-axis, and the y-axis you can see a chains over there on the side. I also like to send a thank you to Professor Fang for just giving us the guidance in this class and inspiring me just to challenge myself and get better. And yeah, until next time, signing out.